Welcome to Earth's final frontier. The deep ocean covers over 70% of our planet, yet an astonishing 95% of it remains unexplored. We have better, more detailed maps of Mars than we do of our own seafloor. The Mariana Trench plunges to nearly 11,000 meters. That's deeper than Mount Everest is tall. At these depths, the pressure exceeds 1,000 times that at the surface. And yet, life finds a way to thrive. Only 4 humans have ever reached the Challenger Deep, the trench's lowest point. Meanwhile, NOAA estimates that 91% of all ocean species are still completely unknown to science. Every year, scientists describe over 1,500 new marine species. Tonight, we descend into genuine mysteries, strange, powerful sounds with no known source, creatures that seem to defy the laws of biology, and disappearances that have no explanation. All of it is documented, all of it is real, and all of it is mysterious. So why have we explored so little? In short, it's incredibly difficult and expensive. Deep-sea exploration can cost even more than sending a mission into space. A single remotely operated vehicle, or ROV, can cost up to $40 million, with a daily operating cost of $50,000. At extreme depths, the crushing pressure would instantly flatten a steel submarine. Only specially engineered titanium spheres can survive. Radio waves don't work underwater, so communication relies on slow, complex acoustic systems. Below 1,000 meters, the darkness is absolute and the temperature hovers just above freezing. The famous submersible Alvin has completed over 5,000 dives since 1964, yet it's explored less than 0.01% of the ocean floor. Despite modern marvels like ROVs and autonomous underwater vehicles, we are discovering new mysteries far faster than we can solve the old ones. To understand where these mysteries occur, we need to understand the ocean's layers. The sunlight zone, down to 200 meters, is where 90% of marine life resides. Below that is the twilight zone, where light fades and bioluminescence begins. Then comes the midnight zone, from 1,000 to 4,000 meters, a realm of total darkness and immense pressure. Deeper still are the abyssal and hadal zones, the latter existing only in the deepest ocean trenches. Now, what makes something a true mystery? It's not just something we don't know yet. A real mystery is a phenomenon that has been observed and documented, but remains completely unexplained, even after intense scientific investigation. Think of the Bloop, an ultra-low frequency sound detected in 1997 that traveled across 5,000 kilometers of ocean. We're focusing on documented facts from top research institutions. No speculation, just science. And real science holds more than enough wonder. Our quest to understand the deep sea is filled with landmark discoveries. The HMS Challenger expedition in the 1870s first proved the deep was teeming with life, discovering over 4,700 new species. In 1938, a fisherman caught a coelacanth, a fish thought to have been extinct for 66 million years. Then, in 1977, the submersible Alvin stumbled upon hydrothermal vents, entire ecosystems thriving on chemical energy instead of sunlight, completely rewriting our biology textbooks. The pressure at these depths is mind-boggling. At 11,000 meters down, it's like having 16,000 pounds pressing on every square inch of your body. It would crush our bones instantly. Yet creatures here thrive. Their cells contain specially adapted proteins, and they have no air-filled spaces that would collapse. How evolution engineered these incredible solutions remains one of the ocean's greatest puzzles. In the perpetual darkness of the deep, an estimated 90% of creatures make their own light. This is bioluminescence, a chemical reaction that creates light without heat. Some use it as a lure to attract prey, like the iconic anglerfish. Others use it to startle predators or find a mate. This remarkable ability evolved independently at least 50 different times, which tells us it offers a huge survival advantage. But with all this life, what do they eat? Food is incredibly scarce. Without sunlight, there's no photosynthesis. Most nutrition comes from marine snow, a slow drift of dead organic material from the surface. Less than 1% of the food produced at the surface ever reaches the abyssal plains. Yet, in this near-starvation environment, biodiversity in some areas rivals that of a tropical rainforest. To survive in the abyss, life has developed some truly extreme adaptations. Many fish are pitch black or even transparent to remain invisible in a world of bioluminescent hunters. Eyes can be enormous to capture the faintest glimmer of light, or they can be completely absent in the total darkness. To conserve energy, metabolisms slow to a crawl, and some creatures can survive for months without a single meal. These adaptations represent millions of years of evolution in an environment that is utterly alien to us. But even here, in the deepest, most remote parts of our planet, we find the mark of humanity. In 2019, explorer Victor Vescovo found a plastic bag at the very bottom of the Mariana Trench. Microplastics are now found in the bodies of creatures living in the Hadal Zone. Deep-sea mining and bottom trawling threaten ancient, fragile ecosystems we've barely begun to understand. Among the ocean's most fascinating inhabitants are its living fossils, species that have remained virtually unchanged for hundreds of millions of years. The coelacanth, for example, looks much the same as its ancestors did 66 million years ago. The frilled shark is another, a relic from 80 million years ago. How did these creatures persist while everything around them evolved or went extinct? The deep ocean's chemistry is just as strange. Hydrothermal vents spew water heated to 400 degrees Celsius, but the immense pressure keeps it from boiling. These vents create unique chemical hotspots that support life through chemosynthesis, entirely independent of the sun. There are also underwater lakes, hypersaline brine pools so dense and salty that they sit on the seafloor like a separate body of water, deadly to any normal sea creature that wanders in. Over the next 2 hours, our journey will take us through 10 categories of genuine deep-sea mysteries. We'll examine bizarre creatures that defy our understanding, geological formations that challenge our models of the planet, and strange sounds recorded by scientists that have no identifiable source. We will venture into the deepest trenches and explore remote underwater mountains. Each section is based on documented scientific research and expedition reports. For some mysteries, we'll explore the possible explanations. For others, there are none. They all invite us to wonder, to question, and to appreciate how much remains unknown about our own world. The journey begins now. Into the deep, into the dark, into the mysterious realm where Earth keeps its deepest secrets. The abyss awaits. It's an environment so alien it might as well be another planet, and the creatures that call it home are so bizarre they shatter our understanding of life itself. We're talking about fish with transparent skulls, sharks that are living fossils, and squid that dwarf a school bus. These aren't monsters from science fiction. They are real animals, documented by scientists, yet they remain shrouded in profound mystery. For centuries, sailors' tales spoke of giant tentacled monsters, the kraken, capable of dragging entire ships to a watery grave. While exaggerated, these legends were rooted in a real creature, the giant squid. Reaching lengths of up to 43 feet, with eyes the size of dinner plates, the largest in the animal kingdom. This behemoth was a ghost. Despite its size, no one had ever photographed a living one until 2004, at a depth of nearly 3,000 feet. The first video footage didn't come until 2012. Even now, we know almost nothing about them. Almost. How deep do they live? How long? How do they breed? Their incredibly complex nervous system suggests a startling intelligence, but we've seen so few, we simply can't know. But the giant squid isn't even the biggest. That title belongs to the colossal squid. While not as long, it is far more massive, potentially weighing over 1,500 pounds. It lives in the frigid, crushing depths of the Antarctic, over 6,500 feet down. Its tentacles are armed with unique swiveling hooks, and its eyes may be the largest to have ever evolved on Earth. We know they exist almost entirely from remains found inside the stomachs of sperm whales, and a single, perfectly preserved specimen captured in 2007. How many are there? We have no idea. Now let's shift to one of the strangest designs in all of nature, the Barreleye fish. For decades, scientists were baffled by it. Specimens brought to the surface were always damaged. It wasn't until 2004 that researchers captured one on video and understood its secret. Its head is a transparent, fluid-filled shield, inside which its tube-shaped eyes can rotate. These green orbs usually point straight up, scanning for the silhouettes of prey against the faint light from above. But when it's time to eat, they can swivel forward. And those things on the front that look like eyes, those are its nostrils. Let's journey back in time with our next two creatures. The Goblin Shark is a living fossil, the last of a family that is 125 million years old. Its long, paddle-shaped snout is packed with sensors that detect the faint electrical fields of its prey in the pitch black. But its most terrifying feature is its jaw. It can launch its entire jaw forward, protruding from its face at incredible speed to snatch a meal. This slingshot feeding is one of the most dramatic predatory adaptations in the ocean. Found between 1,000 and 4,000 feet deep, they are so rarely seen we know almost nothing about their lives. Equally ancient is the frilled shark, a creature so primitive it's been virtually unchanged for 80 million years. With its long, eel-like body and 6 pairs of frilly gills, it looks like something from a prehistoric nightmare. Its mouth is filled with 300 needle-sharp, backward-pointing teeth, perfect for snagging soft-bodied prey like squid. They live at depths up to 5,000 feet, and encounters are exceptionally rare. It's thought their gestation period might last an astonishing 3.5 years, one of the longest of any animal. Now for a creature so unique, it was given its own taxonomic order, a lonely branch on the tree of life, the vampire squid. It's not a true squid or octopus, but shares traits of both. It thrives in oxygen minimum zones, depths where most other animals would suffocate. When threatened, it performs a stunning defense, pulling its webbed arms up and over its body like a cloak, revealing harmless fleshy spines that make it look much larger and more threatening. It can also eject clouds of glowing bioluminescent mucus to disorient a predator. For years, its diet was a mystery, until a 2012 study revealed it feeds on marine snow, the constant shower of organic debris from above, using 2 long, retractable filaments. It's a deep-sea janitor. Just as enigmatic is the Dumbo octopus, named for the ear-like fins on its head that it flaps to gracefully fly through the water. These are the deepest living octopuses known, found as far down as 23,000 feet. Their bodies are gelatinous, and they swallow their prey whole. Due to the extreme depths they inhabit, almost every observation is a world first. The deep sea is full of record holders. The fangtooth has, relative to its body size, the largest teeth of any fish in the ocean. They're so big, it has special pouches in its skull for them to slide into when it closes its mouth. These fish undertake one of the most extreme daily migrations on Earth, traveling thousands of feet up and down the water column every single day. And then there's the pelican eel. Its most prominent feature is its mouth, which is absurdly larger than its body. The jaw is loosely hinged and connects to a stomach that can expand to accommodate prey much larger than the eel itself. Its long whip-like tail ends in a complex glowing organ, likely used as a lure. And of course, there's the internet's favorite sad-looking creature, the blobfish. That saggy, miserable appearance is not what it actually looks like. It's the result of decompression damage. In its natural habitat, 4,000 feet deep, the immense pressure gives its gelatinous body structure, allowing it to float just above the seafloor with almost no effort. It's a perfect adaptation, not a design flaw. Perhaps the most mind-bending creature of all is a tiny jellyfish called Turritopsis dohrnii, the immortal jellyfish. This animal has a biological superpower. When it gets old, stressed, or injured, it can revert completely back to its juvenile polyp stage, essentially aging backward. It transforms its adult cells into a younger state and starts its life over. Discovered in the 1990s, this process of cellular reprogramming has been confirmed in labs, and it has profound implications for our own understanding of aging. While they can be eaten or get sick, they appear to have no natural limit to their lifespan. These living fossils and immortal beings raise huge questions. Why have creatures like the coelacanth or the goblin shark remained unchanged for hundreds of millions of years, while others evolved or went extinct? What is it about the deep sea that has allowed it to act as a refuge, preserving these ancient forms of life? The adaptations in the deep sea push the very limits of what we thought was biologically possible. There are fish that are almost completely transparent, the ultimate camouflage in open water where there is nowhere to hide. There are ice fish in the Antarctic whose blood is clear. They have no hemoglobin and survive on oxygen dissolved directly in their blood. Other creatures have bioluminescent organs with lenses, reflectors and shutters that rival the complexity of our own optical technologies. At the deepest trenches, over 26,000 feet down, snailfish survive pressure that would crush a submarine. Their cells are filled with a molecule called TMAO that protects their proteins from being destroyed. But there's a limit. Scientists calculate that below about 27,000 feet, the concentration of TMAO needed would become toxic, setting an absolute depth limit for fish. These creatures are living on the very edge of possibility. These biological marvels, from immortal cells to pressure-proof proteins, show us how life can conquer any environment. But the mysteries of the deep aren't just biological. Hidden in the darkness, there is also sound. For decades, hydrophones placed across the world's oceans have recorded powerful, bizarre noises whose sources remain completely unidentified. Some are eventually solved, but others persist as acoustic ghosts in the machine. Now we're going to leave the creatures behind and descend into a different kind of abyss, the ocean's unexplained sounds. We'll listen to the recordings that have puzzled scientists for years. From the famous Bloop to the lonely call of the 52 Hertz whale, the ocean is speaking in a language we are only just beginning to decipher. Let us listen to the mysteries hidden. The ocean isn't silent. It's filled with biological sounds, geological activity, and human noise. But it also contains sounds that defy identification. Ultra-low frequency emissions detected across thousands of kilometers, patterns that don't match any known source. These are real recordings from NOAA and other research institutions, documented acoustic phenomena without confirmed sources. In the summer of 1997, an extremely powerful, ultra-low frequency sound was detected by an array of underwater microphones. Named the Bloop, it was picked up by sensors over 5,000 kilometers apart, an extraordinary range suggesting an immensely powerful source. The sound's profile resembled a biological one, rising rapidly in frequency over about a minute. But its sheer volume suggested something far larger than any known animal, leading to wild speculation about massive, unknown sea creatures. Years later, in 2005, NOAA concluded the sound matched the signature of an ice quake, a massive iceberg fracturing and breaking away from an Antarctic ice shelf. However, this explanation is still debated. The Bloop's acoustic signature has unique characteristics that don't perfectly match other known ice events. It became famous, inspiring documentaries and fiction, but its definitive origin remains one of the ocean's great unsolved mysteries. On March 1, 1999, another strange sound named Julia was recorded across the Pacific. It lasted about 15 seconds, a series of rhythmic pulses rising and falling in frequency. It was loud enough for the entire hydrophone array to hear it, and its source was triangulated to the Antarctic coast. Researchers later attributed Julia to a large iceberg, scraping along the seafloor. But the rhythmic quality is unusual, and it doesn't perfectly match other ice events. Then there's upsweep, a sound that has been continuously detected since 1991. It is a series of tones sliding up a scale over and over. It gets stronger in the spring and autumn, and its source is near a region of volcanic activity in the Pacific. While most think it's related to magma movement, the specific source has never been pinpointed, and its seasonal pattern is still a puzzle. And we can't forget the whistle, a sharp ascending sound lasting just 1 or 2 seconds, popping up in the eastern Pacific since the 90s. It doesn't match ice, it doesn't seem biological, and it has no known geological link. It's just there. On May 19, 1997, hydrophones recorded "Slow Down," a sound that decreased in frequency over about 7 minutes, one of the longest unexplained sounds ever. It was detected across the entire Pacific. While some thought it might be biological, no known creature makes a call that long and powerful. The likely culprit is again ice dynamics, maybe a massive iceberg grinding over underwater terrain, but the extreme duration makes it an outlier, even among ice sounds. Another one, the train, recorded on March 5, 1997, sounds just like its name, a steady, low-frequency rumble. Its uniformity is what's weird. Biological and geological sounds usually fluctuate. Its source is a complete mystery. But some mysteries do get solved. For 50 years, a sound called the bioduck, which sounded like repetitive quacking, was recorded in the Southern Ocean. Nobody knew what it was until 2014. By tagging Antarctic minke whales, scientists finally confirmed the quacking was their vocalization. This 50-year-long mystery shows just how incredibly difficult it can be to identify a sound's true source in the vast ocean. Since 1989, a solitary whale has been tracked making unique calls at 52 Hertz, a frequency much higher than the deep rumbles of blue or fin whales. It's often called the loneliest whale, because at that unusual frequency, no other whales seem to answer its calls. It follows a regular migration route in the Pacific, but never seems to interact acoustically with other whales. Is it a hybrid, a malformed individual, or the very last of its kind? No one knows. Despite multiple attempts, including a 2021 documentary expedition that claimed a potential sighting, the whale has never been visually identified. It just continues its lonely song year after year. And it's not the only one. Marine biologists regularly detect whale songs that don't match any known species. In 2014, complex songs were recorded in the Pacific from an unknown source. In 2018, mysterious whale calls near Madagascar baffled scientists. These are clearly biological sounds, but their sources remain anonymous. They might be from undescribed whale populations or known species exhibiting new behaviors. Each new recording adds another voice to a growing library of ocean singers we cannot yet name. Not all mysterious sounds are natural. Underwater earthquakes and volcanic eruptions produce powerful, low-frequency sounds that travel across entire oceans. In fact, about 80% of Earth's volcanic activity happens underwater, hidden from our view, but many sounds thought to be geological lack confirmed sources. In 2018, a seismic swarm near Mayotte, off the coast of Africa, produced bizarre low-frequency signals detected globally. It was likely a new underwater volcano being born, but the exact process is still debated. On top of that, you have anthropogenic mysteries, unidentified human-made sounds, secret military operations, experimental underwater vehicles, and unregistered industrial activities can all create acoustic signatures that puzzle civilian researchers. During the Cold War, both the US and Soviet navies operated secretive underwater systems, whose sounds are still classified. Even today, military activities can create sounds that are mysteries simply because no one will acknowledge them. Sometimes the mystery isn't what made the sound, but who made it and why they're keeping it a secret. The study of underwater acoustics is about more than just solving mysteries. Seismologists use hydrophones to detect earthquakes, and biologists track whale populations by their songs to monitor their health and migrations. The military, of course, uses it for submarine detection. A key part of this is the SOFAR channel, a layer in the ocean around 1,000 meters deep, where sound waves can travel for thousands of kilometers with minimal energy loss. This channel allows us to hear distant events, but it can also make it tricky to pinpoint exactly where a sound came from. The ocean's acoustic environment is incredibly complex. Sounds reflect off the surface and seafloor, bend through different temperatures and salinities, and interfere with each other. Even changing ocean chemistry from acidification might be altering how sound travels, potentially affecting marine life communication over time. Despite decades of study, new unexplained sounds keep appearing in our records, reminding us just how much we still have to learn about what the ocean is saying. The future of acoustic research is advancing rapidly. Distributed arrays of autonomous hydrophones are covering larger areas of the ocean than ever before. Machine learning algorithms are now sifting through vast archives of sound data, identifying patterns that humans might have missed, and potentially discovering entirely new types of sounds in old recordings. This research isn't just about identifying sounds, it's about understanding the acoustic ecology of the ocean, how animals use sound to navigate, hunt, and communicate. But it also reveals a growing problem. Human noise pollution. Shipping traffic alone has increased ambient sound levels in some regions by up to 20 decibels in the last 50 years. That's a 30 to 50-fold increase in intensity. This noise can disrupt feeding, breeding, and migration for animals like whales that depend on sound to survive. Scientists are now exploring conservation strategies, like modifying ship designs and creating quiet zones in critical habitats. The ocean's soundscape tells a story about its health. Learning to read that story fully is why we must keep trying to solve these deep-sea acoustic mysteries. The ocean's acoustic mysteries remind us how much remains unknown. Sound travels far underwater, yet its sources can elude us for decades, or even forever. From the Bloop to the 52 Hertz Whale, from the seasonal upsweep to hidden human-made enigmas, the ocean speaks in languages we're only just beginning to hear, let alone understand. But now, we shift from what we hear to what we see, or rather, what creates its own light in the absolute darkness. Bioluminescence is the ocean's most visible mystery, a phenomenon so widespread yet so incompletely understood that every deep-sea expedition reveals new questions. How do organisms produce cold light? Why did this ability evolve independently over 50 times? What messages are encoded in their flashing patterns? The mysteries of living light await us, illuminating the darkness while deepening the enigma of how life thrives in the abyss. In the deep sea, an astonishing 90% of creatures produce their own light. This extraordinary fact makes bioluminescence the single most common adaptation to life in the abyss. This light is cold, born from chemical reactions without any heat. It happens when molecules called luciferin are oxidized by enzymes known as luciferase. The result? Light, water, and used luciferin. Organisms have evolved at least 8 different chemical families of luciferin, allowing for a rainbow of glows. Most produce blue-green light, which travels best through ocean water. But others can create green, yellow, or even red light. This process is incredibly efficient, converting 80 to 90% of chemical energy into light, compared to a mere 10% for an old incandescent bulb. This remarkable trick evolved independently at least 50 times across the tree of life, in bacteria, fungi, worms, fish, and more. This suggests a powerful evolutionary advantage, and yet, the exact reasons remain a puzzle. Why did so many unrelated organisms all converge on this same brilliant solution? What made producing light so beneficial that it appeared again and again? Despite decades of research, the ocean's living lights still hold many secrets. Consider the female anglerfish dangling her glowing lure, an esker, from a spine on her head. The light comes from symbiotic bacteria living inside. But how do baby anglerfish find the exact right species of bacteria amidst the millions in the ocean? Are they gifted from their mother, or do they find them in the environment? And how do the fish and their tiny light makers coordinate? Some anglerfish control the glow by adjusting blood flow to limit oxygen to the bacteria. But the communication signals between host and symbiont are a total mystery. Then there's the mystery of the dragonfish. Most deep-sea life is blue-green, but these fish produce and see red light. This is a huge advantage, as most other creatures in the deep can't see red at all. The dragonfish use red photophores under their eyes like a sniper scope, illuminating prey that has no idea it's being watched. It's a private, invisible channel. The evolutionary puzzle is staggering. How did red light production and red vision evolve together? Neither is useful without the other. It's a classic chicken and egg problem that scientists are still trying to crack. When the Atolla jellyfish is disturbed, it puts on a spectacular show, a spinning pinwheel of blue light that acts as a burglar alarm. The display lasts for about 30 seconds, creating a beacon visible from far away. The idea is to attract a bigger predator to attack whatever is bothering the jellyfish, a desperate call for help. But does it actually work? We have very little footage, and what we do have is inconclusive. How does the Atolla control the spin and duration so precisely? Why exactly 30 seconds? It's a sophisticated strategy, but its true effectiveness remains one of the deep's many secrets. Equally stunning are the firefly squid of Japan. During spawning season, thousands gather in shallow waters, creating glowing blue clouds visible from the shore. Each squid is covered in light organs, capable of complex patterns. It's likely a form of mating communication, but the specifics are unknown. How do thousands of squid coordinate their flashing? Are they sending messages or just showing off individually? It's a breathtaking natural spectacle that still leaves scientists scratching their heads. So, do these creatures use light to talk to each other? The evidence points to yes, but it's hard to prove. Many species have unique patterns of light organs like fingerprints, which could help them recognize their own kind in the dark. Flashes could signal identity, sex, or warnings. But until we can match specific light patterns to specific behaviors, it's all just a well-educated guess. Even free-living bacteria glow. They use a system called quorum sensing to count their neighbors and only light up when their population is dense enough. But why? The energy cost is huge. One theory is that glowing attracts predators who eat and then disperse the bacteria elsewhere, a form of bacterial hitchhiking. Then there are the dinoflagellates, single-celled organisms that make waves and boat wakes sparkle. Sometimes they form massive milky seas, glowing patches of ocean so vast they can be seen from space. But the reason they glow is still debated. The traditional explanation is that it startles predators, but the high energy cost makes scientists wonder if there's more to the story. The light organs themselves, called photophores, are marvels of evolution. They range from simple clusters of glowing bacteria to complex structures with lenses, reflectors, and even shutters. How did such complexity evolve? A simple glow might be good for camouflage, but you need reflectors and lenses to create a focused beam for signaling. The evolutionary steps from a simple glow to a biological flashlight are still murky. Many fish in the midwater zone use their photophores for an incredible form of camouflage called counter-illumination. They have light organs on their bellies that produce a downward glow, perfectly matching the dim light filtering down from the surface. When viewed from below, their silhouette completely vanishes. They even have light sensors on their backs to measure the ambient light and adjust their glow in real time. It's like a biological dimmer switch. But how did such a complex, integrated system evolve? All the parts, the light, the sensors, the neural control, had to come together at once to be effective. It's an evolutionary puzzle that keeps scientists busy. If 90% of deep-sea life glows, what about the 10% that doesn't? These creatures have found other ways to survive. Some are completely transparent, achieving invisibility without light. Others are pitch black, absorbing any stray photons to avoid being seen. For them, maybe the energy cost of producing light just isn't worth it. Understanding why some species don't glow helps us understand why others do. Many creatures that do glow don't even make the light themselves. They cultivate symbiotic bacteria. This is a classic win-win. The host provides a safe home and food, and the bacteria provide the light. We see this in flashlight fish, ponyfishes, and anglerfish. Their light organs are incredibly sophisticated, with blood vessels for nutrients, reflectors, and even shutters to control the light. Some can even eject their old bacterial colonies and grow new ones, like changing a light bulb. But again, how do the baby fish acquire the right bacteria? How do the host and bacteria communicate? It's an elegant partnership, but its origins and inner workings are still largely a mystery. The sheer diversity of bioluminescence is mind-boggling. It has evolved independently at least 50 times across the tree of life, a testament to its powerful advantages in the dark. Yet the existence of the 10% that don't glow reminds us that there's no single perfect solution for survival. The variety of chemical recipes and control mechanisms we see suggests we're only scratching the surface. This research has already given us incredible tools, like the green fluorescent protein, or GFP, discovered in jellyfish. It's now used in labs worldwide to watch biological processes in real time and even earned a Nobel Prize. What other breakthroughs are waiting to be discovered in the ocean's living light? This field connects chemistry, evolution, and technology. It shows how understanding nature can lead to incredible innovation. Yet for all we've learned, the ocean's glow illuminates our own ignorance just as much as it lights up the deep. Bioluminescence reveals a world of communication, predation, and defense, all playing out in absolute darkness. From the anglerfish's lure to the dragonfish's red spotlight, life has found countless ways to create its own cold light. But all of this relies on energy from food, which is incredibly scarce in the deep. However, there are entire ecosystems that don't depend on sunlight or the food that trickles down from above. Discovered only in 1977, hydrothermal vents gush superheated, mineral-rich water from the Earth's crust. Around these vents, life thrives on a process called chemosynthesis, powered not by light, but by chemistry itself. This discovery completely changed our understanding of life, proving it doesn't need the sun to exist. Now, we'll dive into these strange and extreme worlds to explore the mysteries they hold and what they can teach us about the very limits of life on Earth and possibly beyond. Picture this. February 17, 1977. The submersible Alvin is descending into darkness, 2,500 meters down to the Galapagos Rift. Scientists aboard expect to see nothing but barren volcanic rock. But what they find is not desolation. It's an oasis of life, a bustling ecosystem thriving around vents gushing superheated water. Giant tube worms, 2 meters long, sway in the currents. Swarms of ghostly white crabs scuttle over the seafloor. Strange oversized clams cluster together. All of this living in total darkness miles from the sun. This single dive didn't just discover new animals, it revolutionized biology. It proved that life could flourish without sunlight, powered by chemical energy in a process we now call chemosynthesis. It was, without a doubt, one of the most important biological discoveries of the 20th century, completely rewriting our understanding of where life can exist. So how do these oases form? It starts at mid-ocean ridges, where tectonic plates are pulling apart. Seawater seeps down through cracks in the Earth's crust, sometimes for kilometers, getting closer and closer to magma chambers. Down there, it's heated to over 400 degrees Celsius. The immense pressure keeps it from boiling. This superheated water is like a chemical sponge, dissolving minerals from the surrounding rock: sulfur, iron, copper, zinc. Then, this mineral-rich water erupts back through the seafloor, hitting the near-freezing 2 degrees Celsius ocean water. The temperature shock causes the dissolved minerals to instantly precipitate, creating incredible chimney-like structures. Black smokers belch out dark clouds rich in sulfides, while white smokers release lighter-colored compounds like barium and calcium. Over years, these chimneys can grow several meters tall, creating unique chemical hotspots that fuel these alien ecosystems. At the very bottom of this food web, replacing plants, are chemosynthetic bacteria. These incredible microbes are the primary producers. Instead of sunlight, they use chemical energy. They oxidize compounds like hydrogen sulfide, that rotten egg smell, along with methane and hydrogen, releasing energy. They use this energy to turn carbon dioxide into organic matter. It's photosynthesis, but powered by the Earth's inner heat instead of the sun's light. These bacteria live freely in the water, but also inside the bodies of other animals in a symbiotic relationship. The entire ecosystem runs on this chemical energy from deep within our planet. This discovery blew open the possibilities for life, not just on Earth, but on other worlds without sunlight, like the moons Europa and Enceladus. The most iconic resident of these vents is the giant tube worm, Riftia pachyptila. They can grow over 2 meters long with vibrant red plumes extending from their tough white tubes. Here's the truly bizarre part. They have no mouth, no stomach, and no gut. They can't eat. So how do they live? They have a special organ called a trophosome, packed with chemosynthetic bacteria, up to 285 billion bacteria per gram of tissue. The worm's red plume acts like a lung, absorbing hydrogen sulfide and oxygen from the vent water. Its unique hemoglobin transports both chemicals to the bacteria without letting them react and poison the worm. The bacteria then work their magic, producing all the food the worm needs. This partnership is so successful that Riftia is the fastest growing invertebrate known, growing up to 85 centimeters in a single year. And the weirdness doesn't stop there. Meet the Yeti crab, Kiwa hirsuta, discovered in 2005. It gets its name from its hairy-looking arms, which are covered in bristles that are home to filamentous bacteria. The crab waves its claws in the chemical-rich vent water, essentially farming its own food, then uses comb-like mouthparts to harvest and eat the bacteria. Then there's the Pompeii worm, the most heat-tolerant complex animal on Earth. It lives in tubes right on the sides of black smoker chimneys. Its tail can be sitting in water as hot as 80 degrees Celsius, while its head is in a much cooler 20 degrees. It survives this insane temperature gradient thanks to a fleece-like coat of bacteria that may act as insulation and a suite of specialized proteins that prevent its cells from cooking. And how about seeing without eyes? Swarms of vent shrimp, Rimicaris exoculata, gather around Atlantic vents. They're blind in the traditional sense, but they have a special organ on their backs that can detect thermal radiation. It's essentially infrared vision. This allows them to see the heat from the vent water, helping them stay in the perfect temperature zone. Close enough for their symbiotic bacteria to thrive, but far enough to avoid being boiled alive. It's an amazing example of evolution repurposing a light-sensitive protein, rhodopsin, for heat detection. But what happens when a vent stops flowing? These hydrothermal oases are temporary, lasting only years or decades. When a vent dies, the ecosystem collapses. But when a new one opens, life is quick to colonize. First, bacterial mats form within weeks. Then mobile creatures like crabs and shrimp arrive. Within a couple of years, tube worms and mussels take hold. But how do their larvae find these tiny, isolated spots in the vastness of the deep ocean? It's a huge mystery. Vents aren't the only chemosynthetic habitats. There are also cold seeps, where methane and hydrogen sulfide bubble up from the seafloor at normal ocean temperatures. These support similar ecosystems, often dominated by giant mussels, and can last for centuries. And then there are whale falls. When a whale dies and sinks, its massive carcass becomes an oasis on the seafloor. A single 40-ton whale provides as much organic matter as 2,000 years of normal food fall. Over 50 to 100 years, different communities of organisms colonize it, with the final stage involving bacteria that break down lipids in the bones, releasing sulfides and creating a mini chemosynthetic ecosystem. The bacteria living in these extreme environments, known as extremophiles, are pushing the known limits of life. The record holder for heat tolerance is an archaeon called Methanopyrus candeleri, found living at a scorching 122 degrees Celsius. Others thrive in extreme acidity or under pressures more than 1,000 times greater than at the surface. These microbes force us to reconsider what a habitable environment looks like, fueling speculation about life in the subsurface oceans of Europa or Enceladus. In 2000, scientists discovered a completely different type of vent field, the Lost City. Instead of black smokers, it has towering white carbonate chimneys, some over 60 meters tall and more than 100,000 years old. These vents produce warm, alkaline fluids, rich in hydrogen and methane, not from magma, but from a chemical reaction between seawater and mantle rock. Some scientists believe these conditions are very similar to those on early Earth, and that places like Lost City could be where life itself began. Despite decades of research, fundamental questions remain. Did vent life evolve in the deep sea, or did it adapt from shallow water ancestors? How do some animals accumulate levels of toxic metals in their bodies that would be lethal to almost anything else? Every new dive reveals new species, new biochemical tricks, and new mysteries about life's incredible ability to adapt. These vents don't just host life, they shape the entire ocean. The heat they release, equivalent to thousands of nuclear power plants, drives deep ocean circulation. The minerals they spew, especially iron, act as fertilizer for plankton thousands of kilometers away. They play a crucial role in the global carbon cycle, both absorbing and releasing CO2 and methane. In a way, they are the planet's plumbing system, connecting the oceans, the crust, and the mantle. Hydrothermal vents revealed that life finds a way, proving that the sun isn't the only source of energy. Chemistry alone can power vibrant, complex worlds. From the revolution in biology that began in 1977, we've discovered giant tube worms without stomachs, farming yeti crabs, and shrimp that can see heat. Each discovery is a testament to life's remarkable flexibility. But the extremes of the deep sea give rise to another fascinating pattern: gigantism. In the cold, dark, food-scarce abyss, creatures grow to extraordinary sizes. We'll encounter giant and colossal squids with eyes the size of dinner plates and crustaceans that dwarf their shallow water cousins. Have you ever heard the term deep-sea gigantism? It describes the tendency for species living in the abyss to grow much, much larger than their relatives in shallower waters. Scientists have a few ideas why this happens. It could be that the frigid water slows down their metabolism, giving them more time to grow. Or maybe there are fewer predators down there, allowing them to reach enormous sizes. Another theory is that in a world where food is scarce, a bigger, more efficient body with a lower surface-to-volume ratio is a huge advantage. There's also Bergmann's rule, which observes that animals in colder climates tend to be larger. But the truth is, no single explanation fits every case. Gigantism is a complex puzzle that researchers are still piecing together. Let's start with a true monster of the deep, the Japanese spider crab. This arthropod holds the record for the largest leg span on Earth, stretching up to 3.8 meters from claw to claw. Imagine a crab the width of a small car. Their main body can be 40 centimeters across, and they can weigh up to 20 kilograms. Found at depths of 150 to 800 meters around Japan, these giants can live for a century. But their size comes with challenges. To grow, they have to molt, shedding their entire exoskeleton. For a creature this big, it's an incredibly dangerous process that leaves them soft and vulnerable. So why get so big? A longer lifespan in cold water means they just keep growing for decades. Their immense size likely deters most predators, and it helps them compete for food. They really push the limits of what's possible for an arthropod. Any bigger, and their exoskeletons would likely collapse under their own weight. Now, let's talk about a creature that looks like it crawled out of a sci-fi movie, the giant isopod. These are in the genus Bathynomus, and they can reach up to 50 centimeters long. Compare that to their little cousins, the pillbugs in your garden, which are only a centimeter or two. That's a 25-fold size increase. The largest of them all, Bathynomus giganteus, roams the seafloor from 200 to 2,000 meters down, scavenging on whatever falls from above. Dead whales, fish, you name it. Their large size is perfect for storing energy, which is crucial when your next meal is completely unpredictable. In fact, they can survive for years without eating. One in an aquarium famously fasted for over 5 years. And it's not just isopods. Amphipods, which are normally just a few millimeters long, can also become giants in the Hadal zone, the deepest parts of the ocean. Alicella gigantea, found over 7,000 meters down in the Kermadec Trench, can grow to 34 centimeters. It seems strange that the biggest ones live where food is scarcest, but the trenches act like funnels, concentrating any organic matter that sinks. When a food fall happens, it's a feeding frenzy and bigger is better. Then there's the lion's mane jellyfish. This creature holds the record for the longest animal ever recorded. In 1870, a specimen washed ashore in Massachusetts with a bell 2.3 meters wide and tentacles that stretched an astonishing 37 meters. That's longer than a blue whale. While most aren't quite that massive, individuals with 10 to 20 meter tentacles are common. This incredible length allows them to create a vast net to capture prey. How they manage these massive tentacles without getting them into a tangled mess is still a mystery. One of the most legendary deep-sea giants is the oarfish. As the world's longest bony fish, verified specimens have reached 11 meters, with some unconfirmed reports claiming up to 17 meters. With their long ribbon-like silver bodies and red fins, it's easy to see how they might have inspired tales of sea serpents, especially since they sometimes surface when sick or dying. Living between 200 and 1,000 meters deep, they remain almost a complete mystery. We think they filter feed on plankton, but almost everything we know comes from dead ones that wash ashore. Even more mysterious is the Greenland shark. Living in the frigid Arctic and North Atlantic waters down to 2,200 meters, this shark is the longest-lived vertebrate on the planet. In 2016, scientists estimated one female to be around 392 years old. They grow incredibly slowly, about a centimeter a year, and don't even reach sexual maturity until they're about 150. Their extreme lifespan is thanks to the cold water slowing their metabolism to a crawl. How their bodies resist aging for centuries is a profound biological puzzle. And of course, we can't forget the biggest fish in the sea, the whale shark. Reaching up to 18.8 meters long and weighing 21 tons, these gentle giants are found in tropical seas worldwide. But despite their size, they're full of surprises. We know they feed on plankton, yet they've been tracked diving to an incredible 1,900 meters. Why would a surface feeder go so deep? It's another mystery of the abyss. Have you ever heard of the megamouth shark? It was completely unknown to science until 1976, when one got tangled in a ship's anchor near Hawaii. Since then, we've had fewer than 300 sightings. Reaching about 5.5 meters, they are filter feeders with enormous mouths that might even glow in the dark to attract plankton, though that's still unconfirmed. They follow the daily migration of their food, rising to the surface at night and descending to 200 meters during the day. Their rarity makes us wonder, are they genuinely that scarce, or just masters of hiding? We're still learning the absolute basics about them. But even the megamouth is dwarfed by our next creature. In 2020, off the coast of Australia, researchers discovered a giant siphonophore estimated to be 45 to 50 meters long. This could be the longest animal ever recorded. Siphonophores are strange colonial organisms, made of thousands of individual specialized clones called zooids that work together. Some are for feeding, some for defense, others for reproduction. They drift in long, spiraling chains, trailing tentacles to catch prey. This discovery challenges our very idea of what a single individual is. Interestingly, while many large animals get bigger in the deep, the trend is reversed for bacteria. Deep-sea bacteria are significantly smaller than their surface-dwelling cousins. This is likely because a smaller cell has a higher surface area to volume ratio, making it more efficient at absorbing the scarce nutrients available. It's a great reminder that different rules apply at different scales. So, becoming a giant in the deep sea is a game of trade-offs. The advantages are clear. You can store more energy, you're more efficient metabolically, you can outcompete rivals for food, and you're too big for most things to eat. But there are downsides. It takes a lot longer to reach sexual maturity, meaning you reproduce later and less often. You also need more food overall, and a large specialized body can be more vulnerable to environmental changes. The unique conditions of the deep sea, the cold that slows everything down, the scarcity of food that favors efficiency, and the lack of predators, all push the balance toward larger sizes for many species. But it's not a universal rule. Plenty of deep-sea creatures are small. Benthic organisms that live on the complex seafloor might do better if they're small and nimble. It all depends on the specific ecological niche. Gigantism isn't an inevitability of deep-sea life. It's a specific evolutionary answer to a specific set of problems. These giant creatures have captivated our imaginations for centuries. Sailors' tales of the Kraken were likely based on very real encounters with giant squid. These stories found their way into literature, like in Jules Verne's 20,000 Leagues Under the Sea. This fascination is great for inspiring interest in ocean conservation, but it can also create misunderstandings. You've probably seen movies where the giant prehistoric shark, Megalodon, is still alive. It's entertaining, but it's pure fiction. Unfortunately, these real-life giants face very real threats. Deep-sea fishing has decimated populations of species like the orange ruffy, a fish that can live 150 years. We fished them heavily before we even knew how slowly they reproduced. The 400-year-old Greenland shark is also extremely vulnerable. Deep-sea trawling destroys their habitats. Climate change alters the water conditions they're adapted to, and plastic pollution is found even in the deepest trenches. Protecting these animals requires international cooperation and a lot more research, because for many of them we're in a race against time. Measuring these giants is a huge challenge in itself. Most of the time, we only encounter them after they've died and washed ashore or been caught in nets. A dead body relaxes and stretches, or it might swell or shrink, making accurate measurements difficult. That famous 37-meter lion's mane jellyfish, its tentacles might have been stretched out. This is why scientists now use very careful, standardized methods. We hear unverified claims all the time, like reports of 20-meter giant squid, but the largest confirmed specimen is closer to 13 meters. Why does the exact size matter? Because it tells us about the animal's biology, how much food it needs, its role in the ecosystem, and how to protect it. Are we dealing with a few massive individuals or thousands of moderately large ones? The answer changes everything. And with new technology like remote laser systems and stereo cameras, we're constantly refining our understanding and discovering new size records, pushing the known limits of life on Earth. These giants inhabit many zones of the deep sea, their incredible sizes sculpted by the pressures of their environment. But some of the most extreme adaptations aren't about getting bigger, but about surviving in the most extreme locations on the planet. We're now going to descend past the abyssal plains, below 6,000 meters, into the oceanic trenches, the Hadal zone. Here, the pressure is over 600 times that at the surface, temperatures are near freezing, and food is almost non-existent. Yet, even here, life finds a way. But these creatures aren't giants. Their adaptations are focused on withstanding the crushing force. The Hadal zone, named for the underworld, awaits, holding the secrets of life at the absolute limit of possibility. We're diving into the Hadal zone, named after Hades, the Greek underworld. This realm begins at depths greater than 6,000 meters, or about 20,000 feet. It's a world of perpetual darkness, near freezing temperatures and crushing pressure. While this zone covers only a tiny fraction of the seafloor, it holds some of Earth's greatest secrets. Most of these depths are found within 33 ocean trenches, concentrated in the Pacific's Ring of Fire. These immense V-shaped canyons are formed at subduction zones, where one of Earth's tectonic plates slides beneath another. The most famous of these is the Mariana Trench. It contains the Challenger Deep, the absolute deepest point on Earth, a staggering 10,994 meters down. If you placed Mount Everest here, its summit would still be 2 kilometers below the waves. The pressure is over 1,000 times greater than at the surface. Imagine 50 jumbo jets stacked on a postage stamp. Only a handful of humans have ever been there. The very first, in 1960, saw a flatfish and shrimp, proving life could exist. More recent dives, like James Cameron's in 2012 and Victor Vescovo's in 2019, found new species of prawn-like creatures and bizarre microbes. But they also found something disturbing: a plastic bag and chemical pollutants, proof that our impact has reached the most remote place on Earth. While the Mariana Trench gets the spotlight, it's not the only colossal chasm. The Tonga Trench, northeast of New Zealand, is home to the Horizon Deep, the second deepest point on Earth at 10,882 meters. Here, tectonic plates are crashing together at up to 24 centimeters per year, one of the fastest rates on the planet, making it a hotspot for intense earthquakes. It was near this trench that the 2022 Hunga Tonga Hunga Ha'apai volcano erupted, sending a plume higher into the atmosphere than ever recorded. Then there's the Philippine Trench, the third deepest at 10,540 meters, yet it's one of the least explored. The extreme pressure makes exploration incredibly dangerous. In 2012, the robotic submersible Nereus imploded at nearly 10,000 meters while surveying the trench. Other major players include the Kermadec Trench, the Japan Trench, site of the devastating 2011 earthquake, and the Puerto Rico Trench, the deepest part of the entire Atlantic Ocean. Each one is a unique, isolated world, hiding its own secrets. So what kind of life can possibly survive these conditions? Meet the Hadal snailfish, the undisputed depth champion of the vertebrate world. These pale, gelatinous fish were filmed swimming serenely at 8,178 meters. They have no scales, minimal bone, and are mostly water. Their secret weapon is a chemical called TMAO, which protects their cells and proteins from being crushed. But there's a limit. Scientists calculate that beyond about 8,200 meters, the concentration of TMAO needed would become toxic. The snailfish is literally living on the edge of what's biologically possible for a fish. The true rulers of the Hadal zone, however, are amphipods, crustaceans similar to shrimp. In the deep, they can grow to giant sizes, up to 34 centimeters long. When researchers drop baited cameras, thousands of them will swarm the food within hours, a testament to how these trenches act as funnels, concentrating any organic matter that sinks from above. For a long time, we imagined the deep ocean as pristine and untouched. That illusion was shattered in 2019, when Victor Vescovo found a plastic bag at the bottom of the Challenger Deep. Since then, studies have confirmed that microplastics are everywhere. Scientists analyzing creatures from 6 different trenches found microplastic fibers in 72% of the amphipods they tested. These plastics sink from the surface, becoming part of the food chain in the deepest places on Earth. Even more shocking, these same creatures contain high levels of banned chemical pollutants, like PCBs. Concentrations in amphipods from the Mariana Trench were as high as those found in one of Japan's most polluted industrial bays. The deep ocean is not disconnected. It's the final resting place for our waste, and we're only just beginning to understand the consequences for these unique ecosystems. How do these creatures even function? It all comes down to the molecular level. To survive pressure that would destroy normal cells, Hadal organisms have evolved incredible adaptations over millions of years. Their proteins have special amino acid substitutions that make them more compact and pressure resistant. Their cell membranes are loaded with unsaturated fatty acids to keep them fluid, preventing them from turning into a useless gel. And they produce protective molecules like the TMO in snailfish that shield their cellular machinery. Understanding these piezolites is a hot topic in biotechnology. Pressure-stable enzymes from deep-sea microbes could be used in industrial processes. And research into how TMAO prevents proteins from misfolding could even provide insights into diseases like Alzheimer's. The Hadal Zone is a living library of biochemical solutions to extreme challenges, and we've barely read the first page. The very forces that create these trenches also make them violent and dynamic. Subduction zones are where the world's most powerful earthquakes, or megaquakes, are born. The 2011 Japan earthquake and the 2004 Indian Ocean earthquake both originated in these zones, triggering catastrophic tsunamis. These events cause massive undersea landslides and sediment avalanches that can wipe out entire communities of Hadal creatures. But they might also be a source of life, delivering huge sudden pulses of food to the nutrient-starved depths. This is the paradox of the Hadal Zone. It's incredibly food-poor, yet it supports abundant life. The funnel shape of the trenches helps concentrate food, but it's likely that these periodic catastrophic events play a key role in sustaining these populations. How they find food falls in the pitch blackness over vast distances remains one of the great mysteries. In the twilight and midnight zones of the ocean, bioluminescence is common. But does this living light exist in the crushing blackness of the Hadal Zone? It seems to decline with depth. While some creatures down to 7,000 meters still produce light, it becomes much rarer below 8,000 meters. This might be an energy-saving adaptation. When every calorie counts, producing light might be an unaffordable luxury. Other mysteries abound. How do species travel between trenches that are separated by thousands of kilometers of shallower seafloor? Genetic evidence suggests they are somehow connected, but we don't know how. And why does each trench have its own unique set of endemic species? The trenches are isolated deep-sea islands, each a separate experiment in evolution. Answering these questions requires more expeditions, more samples, and more time as we slowly piece together the puzzle of life at its most extreme. The trenches are Earth's final frontier. Life here exists at the very edge of possibility, in a world of crushing pressure, absolute darkness, and freezing cold. From the ghostly snailfish to the swarms of giant amphipods, every discovery reveals new surprises and new questions about how life can adapt and thrive. These trenches are natural wonders, carved by immense geological forces over millions of years. But the ocean floor holds other strange formations, structures that appear geometric, walls that seem unnaturally straight, and patterns that defy easy explanation. We're now going to explore these underwater anomalies. From the controversial Baltic Sea anomaly to the debated Yonaguni Monument, we'll separate science from speculation to understand what truly lies beneath the waves. What are underwater anomalies? They're structures on the seafloor that look unusual, maybe even man-made, but without any solid proof. Most turn out to be natural formations that we misinterpret through fuzzy sonar images or in murky water, but a few are genuinely puzzling, just waiting for a closer look. Our human brains are hardwired to see patterns. It's how our ancestors spotted predators and found food. But this also leads to something called pareidolia, where we see faces in clouds, or in this case cities in sonar blips. Take the Baltic Sea anomaly. In June 2011, a Swedish treasure hunting team called the Ocean X team found a strange circular shape 87 meters down. Sonar showed a 60-meter wide disk with lines radiating from it and a 300-meter long trail behind it. The media went wild with UFO theories. It looked just like a crashed spaceship. But when geologists investigated in 2012, they found a much simpler answer. It's a glacial deposit, a pile of rocks and mud dropped by melting ice sheets about 140,000 years ago. The circular shape is just a coincidence. The lines are scratches from rocks dragged by the ice, and the trail is just sediment shifted by currents. Despite this clear scientific explanation, it remains a favorite in UFO circles, a perfect example of how easily we can be fooled by a weird-looking rock. In 1987, off the coast of Japan's Yonaguni Island, a dive instructor discovered a massive underwater formation 25 meters deep. It had terraces, flat surfaces, and what looked like sharp right angles. One marine geologist, Masaki Kimura, argued it was a 10,000-year-old man-made complex, a lost temple swallowed by the sea. He points to what he calls tool marks and geometric precision. However, most geologists disagree. They say it's a natural sandstone formation that just happens to fracture along straight lines. There are similar formations on the island itself. Plus, despite all the searching, no tools, no pottery, and no human remains have ever been found. The scientific consensus points to a natural origin. Then there's the Bimini Road. Discovered in 1968 in the Bahamas, it's a line of large rectangular stones that looks like an ancient road or wall stretching for 800 meters. Speculation immediately jumped to the lost city of Atlantis, partly fueled by a psychic who had predicted such a find years earlier. But again, geology provides the answer. It's natural beach rock. This forms when minerals cement beach sand together, and it often fractures into block-like shapes. Carbon dating shows the rock is only about 2,000 to 3,000 years old, way too young to be part of some mythical ancient civilization. In 2001, a Canadian company scanning the seafloor off Cuba's western coast found something incredible. Sonar images that looked like a submerged city, complete with pyramids and buildings, 700 meters deep. But that depth is a huge red flag. For a city to be that deep, sea levels would have had to be 700 meters lower. During the last ice age, they were only 120 meters lower. You'd have to go back over 50 million years, long before humans existed, to find sea levels that low. A follow-up submersible dive took some video, but the images were too fuzzy to be sure of anything. Without more evidence, most archaeologists are highly skeptical. The site remains a mystery, but one that's more unresolved than proven. That same year, in India's Gulf of Cambay, researchers announced another potential underwater city. They found geometric patterns on the seafloor and even claimed to have found worked wood dated to 9,500 years ago. This would rewrite the history of civilization in the region. But the claim quickly fell apart. The worked wood could have just been ancient driftwood, and other scientists argued the geometric patterns were simply ancient riverbeds filled with sand. No definitive artifacts like pottery or tools were ever presented in peer-reviewed journals, and the archaeological community largely dismissed the find. You hear a lot about underwater pyramids supposedly found off Japan or Portugal, but pyramid-like shapes are actually quite common in nature. Volcanoes form cones, and erosion can carve rock into surprisingly symmetrical shapes. Add in poor underwater visibility and low-resolution sonar, and it's easy to see how a natural hill can be mistaken for a lost wonder. But genuine underwater cities do exist. They're just found in shallow water, exactly where you'd expect them from realistic sea level rise. Take Pavlopetri in Greece, a complete Bronze Age town just 3 to 4 meters deep. It has streets, buildings, and tombs. Or Heraklion in Egypt, a major port that sank in the 8th century AD, now resting 10 meters down. Archaeologists there have found temples, giant statues and gold coins. And there's Atlit Yam off the coast of Israel, a 9,000-year-old Neolithic village. These sites are real because they have clear architecture and tons of artifacts, all found at plausible depths. Let's talk about a real lost land, Doggerland. During the last ice age, this was a huge area of dry land connecting Great Britain to the rest of Europe. As the glaciers melted, rising seas slowly flooded it between 12,000 and 6,000 years ago. Today, it lies under the North Sea. Fishermen have dredged up stone tools, mammoth bones, and even a human skull from this area. It was a real inhabited landscape, now lost to the waves. Then we have blue holes. These are giant underwater sinkholes, like vertical caves. The Great Blue Hole in Belize is over 300 meters wide and 124 meters deep. They're incredible to look at and are home to unique ecosystems, but they are a well-understood geological feature. They formed when sea levels were lower and acidic rainwater dissolved limestone, creating huge caverns that later collapsed and flooded. The stalactites found inside some of them prove they were once dry caves. They are natural wonders, not man-made mysteries. One of the most beautiful underwater mysteries had a surprising creator. In 2011, divers in Japan found these intricate 2-meter-wide circular patterns on the seafloor, like underwater crop circles. It was a puzzle until scientists discovered they were being built by a tiny male pufferfish. The male spends over a week tirelessly sculpting the sand with his fins to create this elaborate nest. The beautiful ridges aren't just for show, they help protect the eggs from currents. If a female is impressed with his architectural skills, she'll lay her eggs in the center. It's an amazing example of how something that looks artificial can be a product of natural, and in this case very sophisticated, animal behavior. So, most of these underwater anomalies are just our minds playing tricks on us, fueled by poor visibility and fuzzy data. Our tendency to see patterns, combined with a hope for discovering something amazing, leads us to jump to conclusions. Real underwater archaeology is a slow, careful process. It requires systematic surveys, careful excavation, and analysis of artifacts, things that are missing from almost all of these fantastic claims. Skepticism is crucial in science. Extraordinary claims require extraordinary evidence. These formations, whether they're natural, biological, or just misinterpreted, highlight our fascination with the unknown depths. But the ocean holds a different kind of human-made mystery. These aren't about strange rock formations, but about documented losses, ships that sailed into the horizon and never returned, planes that vanished from radar, submarines that went silent. We know they were out there. We know they were crewed by people with families waiting for them, and then they were gone. We now turn our attention to these genuine disappearances, the lost shipwrecks and ghost fleets whose stories are still waiting to be told from the bottom of the sea. The sea has swallowed countless vessels and aircraft throughout history, and while many are eventually found, some simply vanish without a trace. These aren't just accidents. They're genuine puzzles where ships, planes, and even people enter the vast ocean and cease to exist in our records. Remember, the ocean covers over 70% of Earth, offering endless places to hide evidence, and actively works to obscure it with currents, sediment, and natural processes. Let's start with the haunting tale of the SS Waratah. This passenger steamship vanished in July 1909 between Durban and Cape Town, South Africa, carrying 211 souls. She was brand new, on only her second voyage, but there were whispers about her stability. Some passengers even felt uneasy enough to disembark at Durban. After being sighted by another vessel on July 27th, she disappeared. No distress signal, no wreckage, no survivors. A massive search ensued, covering thousands of square kilometers for months, but nothing was ever found. Even over 100 years later, modern expeditions with side-scan sonar have detected possible wreckage, but identity couldn't be confirmed. Theories range from capsizing in heavy storms, which are common there, to structural failure or a rogue wave. The Waratah, often called Australia's Titanic, still rests somewhere in the Indian Ocean, her fate a century-old mystery. Next up, the USS Cyclops. This US Navy cargo ship disappeared in March 1918 with 306 people, marking the largest non-combat loss of life in US naval history. She left Barbados heading for Baltimore and was never seen again. No wreckage, no bodies, no distress call. Some believe overloading with heavy manganese ore caused structural failure. What's even stranger, her two sister ships, USS Proteus and USS Nereus, also vanished in similar circumstances in 1941, both carrying heavy bauxite ore in the Atlantic. None were ever found. These three disappearances in the Western Atlantic certainly fueled Bermuda Triangle myths, but it's more likely a case of structural weakness under immense cargo loads. Fast forward to a more recent and equally baffling case, Malaysia Airlines Flight 370. On March 8, 2014, this Boeing 777 vanished with 239 people aboard, becoming one of aviation's greatest modern mysteries. It deviated from its Kuala Lumpur to Beijing route, flying south into the Indian Ocean until it ran out of fuel. An unprecedented international search covering 120,000 square kilometers, costing around $150 million, found ancient shipwrecks and unmapped seamounts, but no MH370. Debris later washed ashore on African and Indian Ocean coastlines, confirming an Indian Ocean crash, but the main wreckage and crucial flight data recorders remain undiscovered. It's a stark reminder of how vast and unforgiving the ocean can be. Now, let's talk about the RMS Titanic. We know where she is. Discovered in 1985 at 3,800 meters depth, but mysteries still linger. Why did she break apart? Was it structural weakness or the immense forces of her sinking angle? Her stern is almost unrecognizable compared to the relatively intact bow. New footage in recent years reveals accelerating deterioration thanks to metal-eating bacteria. Experts predict the wreck could fully collapse within decades, returning to sediment, and chillingly, no bodies were ever recovered. The extreme depth and conditions likely scattered or decomposed them. The Titanic continues to provide insights, but time is literally eating the evidence. And then there's the infamous Flight 19. On December 5, 1945, 5 US Navy Avenger torpedo bombers vanished during a training mission off Florida with 14 airmen. Radio calls suggested navigation confusion, with the instructor believing they were over the Gulf of Mexico when they were actually over the Atlantic, flying them further out to sea. Fuel exhaustion and ditching were the likely outcome. A rescue seaplane also disappeared, though its wreckage was later found, attributed to a mid-air explosion. But the 5 Avengers never found. The Navy concluded causes or reasons unknown, further cementing its place in Bermuda Triangle folklore. Despite extensive searches, no confirmed wreckage has ever been matched to Flight 19. The most probable explanation is they simply ran out of fuel and sank rapidly in the deep Atlantic. Submarines also face these deep-sea unknowns. The USS Scorpion, a nuclear submarine, sank in May 1968 with 99 crew in the Atlantic. Its wreck was located in October 1968 at 3,000 meters depth, thanks to acoustic analysis of its implosion sound. So the location is known, but the cause still debated. Official investigations suggested a torpedo malfunction or mechanical failure, but Cold War tensions at the time led to theories of hostile action. The wreck remains classified for national security. It's a partial mystery. We know where it is, but not definitively why it sank. And what about ghost ships? Vessels found adrift, seaworthy, with cargo intact, but everyone on board vanished. The Mary Celeste, discovered in 1872, is the most famous. Food on the tables, cargo untouched, but the crew, captain, his wife, and daughter, gone. A lifeboat was missing. No confirmed explanation. Then there's the Carol A. Deering, found aground off North Carolina in 1921. Food cooking, lifeboats missing, logbook gone. Or the Joyita in 1955, found partially flooded but buoyant, crew and passengers vanished. Theories abound, from piracy to panic, but these remain chilling, unexplained disappearances. Beyond modern losses, imagine the ancient treasures lost at sea. Thousands of ancient shipwrecks, many with immense value, are still undiscovered. Spanish treasure fleets from the 16th and 17th centuries, laden with gold, silver, and emeralds, often sank in Caribbean hurricanes. Mel Fisher famously found the Nuestra Señora de Atocha in 1985 after a 16-year search, recovering over $450 million in treasure. But many others, like the Flor de la Mar, a Portuguese carrack that sank in 1511 with treasure looted from Malacca, remain elusive. Estimated to be worth over $9 billion, it's considered the richest shipwreck never found. These wrecks are often buried under centuries of sediment, with deep water and tropical conditions rapidly disintegrating wooden ships, leaving only ballast stones, cannons, and precious metals. Despite modern technology like magnetometers, the vastness of the ocean means most historical wrecks will likely never be found. World War II also left a tragic legacy on the Pacific seafloor, with hundreds of ships and aircraft lost in major naval battles like Midway and Leyte Gulf. Some, like the USS Indianapolis, sunk by a Japanese submarine in July 1945, were found decades later, in this case by Paul Allen's team in 2017 at 5,500 meters deep. Paul Allen's team also located the Japanese battleship Musashi, one of the largest ever built in 2015. Yet countless aircraft carriers, cruisers, destroyers, and submarines from that era still lie hidden in the deep. Even recent losses underscore the challenges. The Argentine submarine ARA San Juan disappeared on November 15, 2017, with 44 crew. An acoustic anomaly consistent with an implosion was detected, leading to an international search. Exactly 1 year later, Ocean Infinity finally discovered the wreck at 907 meters depth, 400 kilometers from its last known position, far outside the initial search area. The hull was severely damaged, confirming a catastrophic implosion. The case highlights how difficult submarine searches are, even with acoustic data. Currents and sinking dynamics can move wreckage far from where you expect it. So why do these wrecks remain undiscovered, despite our incredible technology? The ocean's sheer vastness is the biggest hurdle. It's 362 million square kilometers of surface, with an average depth of 3,800 meters, holding over 1.3 billion cubic kilometers of water. Deep-sea search equipment is specialized and incredibly expensive. Side-scan sonar, our main tool, covers limited areas per pass. Searching 120,000 square kilometers for MH370 required thousands of passes and years of effort. Autonomous underwater vehicles, AUVs, are slow, need to surface for data, and have limited battery life. ROVs tethered to ships are even slower and more costly to operate. Plus, sediment can bury wrecks over time, and currents can scatter debris over vast areas, making initial search estimates often inaccurate. A vessel might drift kilometers horizontally while sinking to 4,000 meters. The MH370 search, covering an area larger than Greece, found nothing. The ocean's immensity simply exceeds our current search capabilities. Even the Titanic, with its approximate location known, wasn't found for 73 years. Statistical models suggest fully mapping the entire ocean floor at high resolution would take centuries. Until comprehensive ocean mapping, like the Seabed 2030 project, is complete, thousands of wrecks will remain lost, their stories untold, their crews unrecovered. The ocean truly hides countless vessels, ships, submarines, aircraft, lost to storms, warfare, mechanical failure, or just unexplained circumstances. Some mysteries are eventually solved, but many remain open, their wreckage concealed in darkness and depth, defying even our most sophisticated technology and expensive searches. These disappearances remind us that despite satellites and sonar, the ocean remains vast, largely unsurveyed, and perfectly capable of hiding even large objects indefinitely. But the ocean doesn't just hide human artifacts, it also sustains life in the most unlikely places. From toxic hydrothermal vents spewing superheated water to oxygen-depleted zones where most creatures suffocate, to isolated whale carcasses providing decades of sustenance, or even underground brine pools so salty they form underwater lakes. These extreme ecosystems challenge everything we think we know about where and how life can exist. They reveal life's truly remarkable adaptability, thriving in conditions that should be lethal. Join us next time as we explore the ocean, most improbable survival stories, communities existing at the very edges of biological possibility, somehow persisting where chemistry, physics, and common sense suggest nothing should live. In some of the most hostile places on Earth, where there's little to no oxygen, a soup of toxic chemicals, scorching heat or freezing cold, and virtually no food, you wouldn't expect to find anything alive. Yet, in these extreme ecosystems, specialized communities don't just survive, they thrive. They are a testament to life's incredible resilience and adaptability, showing us the very limits of biology and hinting at what life might look like on other worlds. Let's start with oxygen minimum zones, or OMZs. These are vast regions of the ocean where the dissolved oxygen levels plummet, creating hypoxic conditions that are lethal for most marine animals. They naturally occur between 200 and 1,000 meters deep, in areas with poor circulation where decaying organic matter sucks up oxygen faster than it can be replaced. Huge OMZs exist off the coasts of Peru, California, and West Africa. But even here, life persists. The vampire squid, for instance, has special blood that efficiently binds to what little oxygen is available. Other fish have evolved larger gills, and unique bacteria can produce their own energy from toxic sulfides. These creatures have essentially mastered the art of living in slow motion, with reduced metabolic rates to conserve every precious molecule of oxygen. Alarmingly, climate change is causing these dead zones to expand, threatening fisheries and squeezing marine life into ever smaller habitable spaces. Now, imagine an underwater lake. That's a brine pool. These are pockets of water on the seafloor that are 5 to 8 times saltier than the surrounding ocean. Because they're so dense, they form distinct pools with their own shorelines. Discovered in the Gulf of Mexico and the Mediterranean, they form when ancient salt deposits dissolve and seep upwards. For most animals, swimming into one is a death sentence due to the toxic salinity and lack of oxygen. They are quite literally pools of death. But right at the edge, specialized mussels and bacteria flourish, feeding on the methane and hydrogen sulfide bubbling up from below. These pools also act as incredible time capsules. Anything that falls in is perfectly preserved for centuries. Another fascinating feature is the cold seep. Unlike scorching hydrothermal vents, these seeps release methane and hydrocarbons at the same chilly temperatures as the deep sea. Found on continental margins around the globe, they support entire ecosystems teeming with giant mussels and tube worms. The foundation of this life is bacteria that consume methane and sulfides, often living symbiotically inside the animals themselves. Cold seeps can last for thousands of years and play a crucial role in our climate, acting as natural filters by consuming massive amounts of methane before it can reach the atmosphere. And then there's the whale fall. When a massive whale dies and sinks, its body creates an oasis of life on the barren seafloor that can last for a century. A single 40-ton carcass provides the same amount of organic matter that a similar patch of seafloor would receive in 2,000 years. This triggers a succession of stages. First, scavengers devour the soft tissue. Then, opportunists colonize the bones. Finally, for the next 50 to 100 years, bacteria break down the lipids in the bones, releasing sulfides that support a chemosynthetic community similar to those at vents and seeps. Over 400 species have been found at whale falls, some of which exist nowhere else on Earth. Have you ever heard of a false bottom in the ocean? During World War II, sonar operators were baffled by a mysterious layer that appeared on their screens, which they mistook for the seafloor. This was the deep scattering layer, a dense concentration of billions of fish, squid, and krill. This layer performs the largest daily animal migration on Earth. Every single night, these animals ascend towards the surface to feed, and every day, they descend to the darkness between 400 and 700 meters to hide from predators. The sheer biomass involved is staggering, an estimated 10 billion tons of animals, more than all terrestrial wildlife combined. This daily migration is also a vital part of the ocean's biological pump, transporting massive amounts of carbon from the surface to the deep, which helps regulate our climate. It's a beautifully synchronized yet mysterious daily dance. Even deeper, in the Hadal zone below 6,000 meters, life somehow flourishes in what should be a food desert. The secret lies in topography. The V-shape of ocean trenches acts like a funnel, concentrating sinking organic matter from vast areas above. Earthquakes can trigger underwater avalanches, delivering sudden feasts. Carcasses and other dense items also accumulate here. When scientists drop baited cameras, they are swarmed by thousands of amphipods within hours, suggesting an incredible ability to detect food from miles away. But many mysteries remain. How do these dense populations survive between these rare food falls? It suggests a level of metabolic efficiency that we are only just beginning to understand. In these harsh environments, teamwork is everything. Symbiotic relationships are key to survival. At vents and seeps, many animals like the giant riftia tube worms have no digestive system at all. They rely entirely on bacteria living inside them to convert toxic chemicals into food. The mussels and clams found here also host these chemosynthetic powerhouses in their gills, getting most of their nutrition from their tiny partners. The evolution of these partnerships is a marvel. How did two separate organisms become so intertwined that one cannot live without the other? It's a multi-million-year story of coevolution, genetic coordination, and synchronized reproduction. These partnerships push the boundaries of life, but extremophile bacteria rewrite the rulebook entirely. There are thermophiles that thrive at 122 degrees Celsius, psychrophiles that live in frozen sea ice, acidophiles that survive in battery acid conditions, and barophiles that require crushing pressures to live. These incredible microbes expand our definition of a habitable zone, making places like the subsurface oceans of Europa and Enceladus seem like plausible locations for life beyond Earth. On the seafloor, you can find living carpets known as microbial mats. These layered communities are Earth's oldest known ecosystems, dating back 3.5 billion years. Each millimeter-thin layer contains different types of bacteria that work together to cycle crucial elements like carbon, nitrogen, and sulfur. They are tiny, self-contained worlds, and these ecosystems are surprisingly resilient. When a hydrothermal vent dies, its community collapses, but a new vent can be colonized and a mature ecosystem re-established within a decade. However, this natural resilience has its limits. The threat of deep-sea mining looms large, promising a level of destruction far beyond any natural disturbance. Mining test sites from 40 years ago still show visible scars with virtually no recovery, a stark warning about the irreversible damage we could cause. These deep-sea ecosystems are not isolated islands. They are interconnected by a web of ocean currents that disperse larvae, animal migrations that transport nutrients, and whale falls that act as stepping stones between habitats. This connectivity means that a disturbance in one area can have ripple effects across thousands of kilometers. And beneath the seafloor itself lies the deep biosphere, a vast hidden world of microbes living in sediments and rock, potentially making up 70% of all bacteria on Earth. These organisms live life in the ultra-slow lane, dividing perhaps once a century. Their full impact on global cycles is still a profound mystery. Even the deepest parts of our ocean are not immune to climate change. Warming surface waters are slowing down the ocean conveyor belt, which delivers oxygen to the deep sea. This, combined with warmer water holding less oxygen, is expanding the oxygen minimum zones. Ocean acidification threatens corals and other shell-building animals that create vital habitats. Warming could also destabilize massive deposits of methane hydrates on the seafloor, releasing a potent greenhouse gas and creating a dangerous feedback loop. The deep ocean has been our planet's silent buffer, absorbing enormous amounts of heat and CO2. But this service comes at a great cost, and we are rapidly altering a world we barely comprehend. These extreme ecosystems reveal life's incredible tenacity. From bacteria that create food from poison to communities that rise from the dead, life always finds a way. But notice a common thread. All of this biology depends on geology. Tectonic plates create vents, sediments release methane, and subduction zones form trenches. Geology sets the stage, and biology writes the script. As we conclude this exploration of life, we now turn our focus to the geological mysteries of the ocean, the powerful forces that shape our planet from below. First up, let's talk about the dynamic seafloor. It's not just a flat bottom. It's a constantly moving landscape shaped by tectonic activity, volcanic eruptions, and chemical processes. Imagine new seafloor being born at mid-ocean ridges, stretching for 65,000 kilometers. That's the longest mountain range on Earth. Here, magma rises, creating new crust. But even with all we know, why do some parts spread super fast at 15 centimeters a year, while others crawl at 2? And why do these ridges look so different from each other? These are big questions that keep scientists busy. Now picture towering underwater mountains called seamounts. Over 100,000 might exist, but we've barely mapped 9,000 and studied even fewer. Each one is a unique ecosystem, a hotspot of biodiversity, often with species found nowhere else on Earth. It's like finding a whole new world every time we explore one. And then there's fire ice, methane hydrates. These ice-like solids hold a staggering amount of carbon, more than all fossil fuels combined. They're stable under immense pressure and cold, but what happens if the ocean warms? A massive methane release could create a dangerous feedback loop, accelerating climate change, a truly scary thought. Did you know that 80% of Earth's volcanic activity happens underwater? Most eruptions go unseen, but when they're big, they're really big. Remember the 2022 Hunga eruption? It shot material 58 kilometers into space, the highest plume ever recorded, and triggered a massive tsunami. And speaking of massive, submarine landslides can move incredible volumes of sediment. The Storegga slide off Norway 200 years ago was so huge it caused a tsunami that devastated Stone Age communities. Even more eerie are rogue waves. For centuries, sailors dismissed them as myths, until the 1995 Dropna wave struck an oil platform, measured at a staggering 26 meters. Satellite data now confirms these sudden monstrous waves are more common than we ever imagined, and predicting them is a huge challenge. Moving on to ocean trenches, formed where one tectonic plate dives beneath another. These are the deepest parts of our ocean, but how does this process even start? And why do some plates dive steeply while others just graze the surface? Even more puzzling are the magnetic stripes on the seafloor, alternating bands of normal and reversed magnetism that act like a giant geological barcode. They were crucial in proving seafloor spreading, but why does Earth's magnetic field flip? It's a mystery tied to the swirling liquid iron in our planet's core, and these reversals can take millions of years with no clear pattern. Below the surface, beyond the trenches, lie the vast abyssal plains, covering over half of Earth's surface. These incredibly flat regions, 3 to 6 kilometers deep, seem barren but teem with life, from sea cucumbers to unique bacteria. They play a massive role in storing carbon, but we're still figuring out just how much. And scattered across these plains are polymetallic nodules, potato-sized lumps rich in valuable metals like manganese, nickel, and cobalt. These form incredibly slowly, growing millimeters over millions of years. How do they stay on the surface without being buried by sediment? It's another deep-sea enigma. These mysteries, from varying ridge speeds to strange seamount life, methane hydrate stability, volcanic forecasting, landslide triggers, rogue wave prediction, subduction initiation, magnetic reversals, abyssal biogeochemistry, and nodule formation, all represent active frontiers of science. We've made huge leaps with autonomous underwater vehicles, deep-sea drilling and satellite mapping, but the ocean's sheer vastness and extreme conditions still limit us. The Seabed 2030 project aims to map the entire ocean floor by 2030, revealing countless new features. The more we learn, the more questions we uncover. The ocean's mysteries aren't shrinking, they're expanding, and that's incredibly exciting. This leads us to a really contentious issue: deep-sea mining. Those polymetallic nodules? They hold metals vital for our tech, batteries, and renewable energy. Proponents say it's better than terrestrial mining, but opponents warn of devastating, irreversible damage to ecosystems that took millions of years to form. Early experiments from the 1980s show no significant recovery after 40 years, and we haven't even described most of the species down there. Destroying habitats before we understand them means losing potential medicines and scientific knowledge forever. It's a huge debate between massive economic potential and potentially catastrophic environmental consequences. And beyond mining, Our deep oceans face threats from bottom trawling, overfishing, climate change leading to warming, acidification, and deoxygenation, and even plastic pollution in the deepest trenches. Protecting this incredible realm requires global cooperation, because these ecosystems don't respect national borders. So as our journey through these geological mysteries wraps up, it's clear that understanding our planet is a never-ending quest. The seafloor is a living, breathing part of Earth, constantly creating, destroying, and influencing everything from ocean currents to our climate. It holds clues to Earth's past and resources vital for our future. Yet we've only mapped about 25% of it in high resolution and explored even less directly. The interactions between geology, chemistry, biology, and physics down there are incredibly complex, and we're only just scratching the surface. What we've learned today is truly remarkable, but what we don't know is humbling. The ocean, covering most of our world, still holds secrets that are just waiting to be discovered. The journey continues, and it's an adventure of a lifetime. Over the past 2 hours, we've descended into Earth's final frontier, exploring genuine mysteries documented by science, but not yet fully explained. We've encountered creatures whose biology seems impossible, giant squids with eyes larger than dinner plates, and fish with transparent heads. We listened to the ocean's unexplained sounds, the bloop, detected across thousands of kilometers, and the lonely 52 Hertz whale, singing a song no others seem to answer. We witnessed the living light of bioluminescence and discovered entire ecosystems thriving without a single ray of sunlight, rewriting our understanding of what life requires. These aren't fantasies, they are documented phenomena, yet the mysteries remain. The deep ocean continues to surprise us with each expedition, each new technology, and each dive into the darkness. Consider what remains unexplored. 95% of our ocean. We have better maps of Mars than our own seafloor. NOAA estimates that 91% of ocean species are still awaiting discovery. That is potentially 2 million species unknown to science. The Census of Marine Life, a decade-long effort by thousands of scientists, found 6,000 potentially new species, yet barely scratched the surface. Vast regions remain completely unsurveyed. Imagine exploring a landscape where it takes 2 hours just to travel from the ground to the surface. What discoveries, what creatures, and what new mysteries are waiting for us in that vastness? So why should we care about these deep-sea mysteries? Well, scientific knowledge drives human progress. Understanding how life adapts to extreme pressure or survives without sunlight has practical applications. Bioluminescent chemicals are now used in medical imaging tools. Enzymes from deep-sea bacteria are used in industrial processes. Future discoveries might yield new medicines or materials we can't even imagine yet. And on a larger scale, the ocean absorbs 90% of our planet's excess heat. We cannot protect what we don't understand, and that's why mystery drives exploration, exploration drives knowledge, and knowledge enables wise decisions for us all. Fortunately, our technology is advancing rapidly. Autonomous underwater vehicles can now navigate on their own for months, mapping the seafloor. Environmental DNA allows scientists to identify species just from a water sample. New materials let us dive deeper than ever before, making the deepest places on Earth accessible. The Seabed 2030 project aims to map the entire ocean floor by 2030. As technology improves and costs decrease, the pace of exploration will only accelerate. The next decade may reveal more about the ocean than all of previous history combined. However, the deep ocean is profoundly affected by climate change. Warming waters, decreasing oxygen levels, and ocean acidification threaten ancient ecosystems that have been stable for millions of years. The deep ocean has been our planet's buffer, absorbing immense amounts of heat and CO2. But this service comes at a tremendous cost to its delicate ecosystems. We are altering systems we barely understand, which makes ocean research not just interesting but urgent. The ocean's health truly determines the future of our planet. The deep sea also faces direct threats from human activities. Bottom trawling destroys ancient coral gardens, deep-sea mining proposals threaten fragile habitats, and pollution, from plastics to chemicals, is found even in the deepest trenches. Yet protection is minimal. Less than 8% of the ocean is protected, mostly in coastal areas. The recent UN High Seas Treaty is a step forward, but it needs to be put into action. The challenge is to balance our needs with protection, guided by science. This requires political will, public support, and continued research. No single nation can tackle this alone. Ocean exploration requires international collaboration. Research vessels are incredibly expensive, so data sharing is key. Global projects like the Census of Marine Life and Seabed 2030 bring together thousands of scientists from across the world. While political tensions can create barriers, the health of our shared ocean demands that we work together, transcending national interests for the collective benefit of the planet. It's a difficult challenge, but a necessary one. And you can be a part of it. Ocean exploration isn't just for professional scientists. Citizen science allows the public to participate in discovery. Divers document species, and projects even let video gamers help solve molecular puzzles. Public interest, fueled by documentaries and social media, drives funding and political support for conservation. When people understand the ocean's mysteries and its importance, they are more likely to support its protection. The ocean's mysteries belong to all of humanity. Some of these mysteries may be solved sooner than we think. Improved sonar might finally locate lost vessels. Genetic sequencing could identify the 52 Hertz whale, yet solving one mystery often reveals a new one. Discovering giant squid led to questions about the even larger colossal squid. That's the beauty of science. The more we discover, the more we realize how much we don't know. The ocean's mystery isn't shrinking, it's expanding. The ocean has shaped our past, and it holds our future. It covers 71% of our planet, produces most of the oxygen we breathe, and regulates our climate. We are not separate from the ocean. We are deeply connected to it, dependent on its health for our own survival. Understanding the deep ocean is about understanding our place on this water world. So, what does the future of exploration look like? Imagine swarms of tiny robots mapping vast areas, or underwater habitats where scientists can live for months at a time. Picture AI that identifies new species in real time. But perhaps most importantly, a future where we shift from exploitation to stewardship, treating the ocean as a vital ecosystem to protect. This isn't science fiction. It's the future we are building right now. As our journey ends, remember that every breath you take connects you to the ocean. The mysteries of the deep aren't just abstract curiosities. They are essential clues to understanding our world and ourselves. Wonder generates care, and care generates action. The ocean's mysteries inspire us, but its vulnerability demands a response from us. The journey doesn't end here. It continues with every question asked, every mind engaged, and every action taken to protect this vast, mysterious, and vital part of our planet. The exploration continues. The ocean awaits.